this group can be generated by these elements here in the minimal generating set. Okay? By definition, that's what this is, right? Its function is to generate all possible elements, X, of your group, your abelian group now. Okay? So that means that this is true here. This. Okay? So that means X can be written in this form. That's what a generating set does, right? So any X can be written in this form. Now we now have to show that. So these integers are here. We have to show that they can take values only 0 or 1. All right. Now that's the general form, right? That follows just from the fact that this set here is your minimal generating set. Right? It'll be of this form. Okay, now let's use this property. And we'll be able to show that these R's now can only take the value 0 or 1. Okay? So how to prove that? Well, these R's in general, they'll be of the form K2 plus 0 or plus 1. They'll be of that form. Okay. So in other words, R is it's an integer, so it's odd or even. Okay. So if it's even, it'll just be of the form 2k, and k is just an integer. Right. Now if it's odd, it'll be of the form 2k plus 1. Right. Now the 2 here, that's the order of your element. Okay. So for any of these A's, so just generate AI to the R, will be of the form AI 2k plus 1 or plus 0 if you like, right? Now, so that's A to the I, now squared, okay, just put the 2 inside, AI to the 1 or to the 0. Okay, so just this is just exponents. Now a to the I squared is e, right? So this is just e to the k, and this here is a to the I epsilon, right? We call that epsilon I. Now this takes the value either 0 or 1, all right? Now e to the k is just e, right? So it's just, what you're left with is a to the I e to I, right? And that is of this form. So each of these boils down to this, where of this epsilon form, which this integer here is either 0 or 1. Okay, and that boiled down to that as a result of this, the result that all the elements, well except the unit, all the elements have order 2. Okay, so these R's reduce to epsilons, in other words 0 or 1. So from this we get that. Okay, so we have a solution. So existence done. Right, now proving uniqueness is quite a bit trickier, and I'm going to, let's see, I can do some. As usual, I'm running out of board. Oh, by the way, I went to the store where I'm to buy the larger board, and the factory that the store orders from had run out of stock, and so they're now making some more. So hopefully tomorrow, next day, I'll be able to get a new board, so all this will have gone, will all be nice and white, and 30 centimeters longer, same height, right? So that'll be certainly be helpful. All right, now look, we will now try to prove uniqueness, right? Because you asked in the theorem uniqueness. You're asked to show that expressing it this way, there's only one way you can do it. So in other words, for a given element, these etas are given, right? They're fixed. You can't rearrange them. They're either, like for a particular x, this will be either 0 or 1. This one will be either 0 or 1, and so on. And these etas will be fixed given x. You specify the x, these etas will then be determined, right? Uniquely. There's only one way to do it. All right. So how to show that? Well, let's assume that there's another way of doing it. So we'll just assume that there's a second form. So we'll rewrite x and we'll call it delta 1, a to delta 2 dot dot dot, a to the n delta n, right? So we're assuming that there's a second way to write this. And you can probably sense this is the beginning. This is the beginning of an argument, reasoning by contradiction. So we'll assume that there are two forms, that it's not unique, and then we will deduce a contradiction. And therefore, because of that contradiction, we go back to the original assumption that there were two distinct ways to write a given element and reject it. So that means there's only one way. Now we know there is a way because we've already proven the existence. So if there's not two, and we know there's one, well there must be, therefore there's only one. Okay. All right. So that's the strategy. So we will let this be equal to this. So I'm running out of board. So the assumption is, assume there are two ways to express this, right? So that means this right-hand side equals this right-hand side. So we can say then that A1 epsilon 1 A2 epsilon 2 dot 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 AN epsilon n equals A1 delta 1 A2 delta 2 dot 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 AN delta n. Right? Now let's assume we go down quite a bit before, and they're all the same. So for the first, let's say, so that'd be like the first position. That's the second position. That's the nth position, and so on. Let's say this epsilon here is the same as this delta, and this second one's the same as that one, and so on. And we just go down, and they're all the same until we meet our first difference, right? If they're all the same, if all these etas are the same, if eta 1 equals delta 1 and eta 2 is delta 2 and so on, if they're the same all the way down, right to n, well, then this is not different from that. Okay? Now we're assuming it is different. So somewhere, at some position, there must be a difference. There must be some eta that's different from a delta. Okay? So let the first one, as you go from left to right, as you go down, the first one that we meet, let it be at the rth, the letter R, the rth position. Okay? So at rth position, POSN, eta to the r is not equal to delta to the r. All right? So we go down here and we meet our first difference. So it will be at a to the r, AR to the epsilon r. And here we'll have AR to delta r. So e to the r is not equal to delta to the r. That's the first time you get a difference. So that means all these alphas here before are equal. Does that make sense? I mean, this whole thing is equal, right? And our first difference occurs, I don't know, here somewhere in the middle, let's say, like here. So that means all these terms before this difference, they're just the same as this product here before you meet the rth position. So the first position, the product of the first position, second position to r minus 1 here is equal to the product here of the first position, second position, until a of r minus 1. So let me write that out explicitly, make it a bit clearer. Actually, I've run out of boards, so I'll stop and clean a board and continue.